Hi folks, welcome back to yet another exciting video. So some of us might have actually looked at this type of thing before, but that may have been a while ago and we are looking at applications, so we need to bring it back on board. So here we've seen this gradients of tangents to curves, so here we go, just maybe get a little picture here. Um, so what we're actually looking at here is, well, we've got a line and a curve and it's the same, they share the same x value um, where the line is tangent to the curve. So locally, um, we've got a tangent there to the curve. And so what I mean by locally is, well, we don't know what's going on with the curve to the left or right. So what if it was actually extended a little bit there? And so that means we'd have a tangent to curve locally there and with a tangent to the curve locally there. Right, so that's fine. But let's go back to um, that scenario there. So, and here, just to emphasize, the gradient of the line, which I'm referring to as M, and so I'm just using the dash notation here, and the x value is A, so that's why I put that in. So the gradient of the line is actually equal to the gradient of the curve as well at that point. So let's just go some curve x cubed, and we want to evaluate the tangent or the gradient of the tangent of that curve. So there's a picture here. X is 1.5, f of x is x cubed. So we need the derivative here, because the derivative dy by dx, changing y over the change in x, that gives you the gradient of both the tangent line and the curve. So just take the f is equal to x cubed. It's going to differentiate it using the dash notation. That gives you 3x squared. You remember the rules for differentiating here. And so what we're going to do, we know the x value is 1.5. So that's m. So I'm using the dash notation here for the derivative. Putting 1.5 in place of x, so that'll be 3 times 1.5 squared. Put that in there and go and get an answer. So the gradient of that tangent line at the curve is exactly 6.75. Okay, and fractional answers would be fine in this case. That'd be okay. Here in another scenario, what we've got here, um, we'll get a sine curve, y equals sine x, and we're looking at the x value of pi over 3. So here, whenever trigonometry meets calculus, we'd be dealing in radian measures, so we need to watch for that. Anyway, let's go and get a wee picture here. That's y equals sine x, and just one wavelength, one period between 0 and 2 pi, and it maximizes at 1, minimizes at -1. So we were looking at pi over 3, so here's the situation, there's the value. Just went up to the curve and put in a line there, a tangent line, and that's kind of roughly what it is here. So in order to get the gradient there, we need to differentiate the curve, differentiate sine x, and then just pop in the value of x equals pi over 3. So there's the curve, sine x, differentiate it, make sure you're using the correct formula. So here we've got the derivative, it's cos x, and we know the value of x that we're looking for here is pi over 3. So if we just go and take pi over 3 and pop that into the derivative, it should give you back the gradient. Okay, so cosine of pi over 3, make sure your calculator's is in radian mode, or maybe you remember this is a common angle, pi over 3, which is equivalent to 60 degrees. So just pop that in there, and it gives you out a nice answer of a half. Yeah, that's fine. Here we go for another one. I'm not going to give you a picture here, but what I just want to emphasize here that we're dealing, the variables we're dealing with is q and t. That would just be like if we had x, it'd be 2 pi, and 2 pi is just a number, times x plus whatever that is at the end, pi over 4, that's a thing called a phase angle. Right, so that it'd be equivalent to that there. Okay, so let's go and just go and differentiate this because I'm looking for the rate of change here. Rate of change, that's the gradient. So I've got a value of t is equal to 3s, 3 seconds maybe. So let's go and q dash or dq over dt. Okay, changing q with respect to t, and hopefully you remember the rules for differentiating. So whatever's in front of t, it comes out the front and it multiplies at 10. So 2 pi times 10 is 20 pi. Cosine goes to negative sign when we're differentiating it, and the contents in the bracket stay the same. Okay, so there we've got our derivative. So let's go and get the value of t, which I think was 3 seconds. So 3 seconds here. Just go and plug that in and fire that in. Maybe simplify the contents of the larger bracket. It's up to yourself. If your calculator can cope, then go for it. So here, I've fired that in, and it gives me that answer there. So whatever dq by dt is, right? And maybe your calculator, if it was in a certain mode, would give you that there, negative 10 times root 2 pi, right? Either or. Okay, and so you can always rewind this and have another wee look. Right, so we're going to talk about stationary points. So here, stationary points. So these are points on curves or functions where the derivative is exactly 0, as I'm saying here. Okay, this our condition, dy by dx, or whatever it is equal to 0. Right, so we get different types of stationary points. What we've got here is what's called a local maximum turning point, horizontal line. It's got gradient 0. Okay, so another one, we've got minimum turning point. I'm just putting a tangent line on it there. It's horizontal. A rising point of inflection. Okay, so it's rising left to right, but it bottoms out in the middle there, where the gradient is exactly 0, and its kind of mirror image is that one there, falling point of inflection. Okay, so it's falling left to right, and in the middle, it just seems to achieve a gradient of 0 there. So there, that's the 4 types we're going to look up for stationary points. And for our stationary points, the derivative is always equal to 0. That's what our condition. So we're going to take a function, get its derivative, make it equal to 0, then we'll be able to see what type is it, what type of turning point or point of inflection the bottom two are. Right, let's go for it. So get a nice wee example here. So this example here, x squared take away 5x plus 6, and it's in state its nature. So that's the type of turning point that we're looking at here, stationary point. Right, so let's go and take it, differentiate it. We know the rules by now. Okay, so stationary points exist where there's a condition dy by dx, the derivative is equal to 0. Okay, we've got a derivative, we've got a condition that's equal to 0, force them together. Go and solve for x. Okay, so that's as we've come up with x equals 2.5 there. And so we're now going to use a nature table with this x equals 2.5. And usually we refer to this single x value, or sometimes we've got more, as the critical value or the critical values there. Right, so this is our nature table here. We've got kind of we've got 3 rows. So top row here that's all x values we're interested in. Next row, that's all with derivative values. And last row there, that's the nature of the shape of the curve, or what's happening in the curve. So let's go for it. And we're going to look left and right of the critical value here. So we're just going to pick numbers. Pick nice numbers. So a number for x to the left of 2.5 and a number to the right of 2.5. I'll probably pick 2 and 3 here. You can go to half either side. You pick whatever numbers you want. You could pick 1 and 4, 0 and 16, whatever. So what we're going to do here is we're going to examine these numbers, 2, 2.5 and 3 in the derivative. Well, we know what's happening at 2.5. Okay, so that's saying just evaluate using the derivative. At 2.5, we know the derivative is 0. That's how we actually come up with the x value of 2.5 before start. So we need to go and use this derivative here. So be careful with the buttons. So I've just put in value of 2 into the derivative, 2x take away 5. And I'm just interested in the answer there. It's -1, so I'm interested in that negative there. I've done the same with 3, put it into the derivative. I'm interested in the answer. Usually I just write down 1, but I'm interested in the sign. So I've got two answers for 2 and 3, -1 and 1. So go and take the signs and put them in there. Because that's what I've done there. So those signs, they relate to the slope of the curve, or the nature. So that's what I'm going to establish it here. So we're looking at the signs here, and we'll just basically think about gradients and think about lines. So if you've got a negative gradient, the line would go down left to right there. If you've got a zero gradient, it'd be going straight across horizontally. Lastly, positive gradient, it'd be going up there. So that looks as if it's kind of tracing out like a minimum turning point. That's what it looks like here. So here, what we're going to say is we've got a minimum turning point at x equals 2.5. Right, here's another one. So we get 2x cubed, take away 15x squared plus 36x. And again, we're going for the nature. So, let's go for it. So take the curve, differentiate it. Okay, so just go through and double check that that's correct. Right, we've got a derivative. So, we're looking for the stationary points. So, like it says, there's our condition that exists where the derivative is equal to 0. So, that's exactly what we're going to do here. Take that was just check that was for derivative. Yep, it was. We're going to force it, make it equal 0. We've done it. Okay. So you've got a quadratic equation there. You can solve it any way you want. You could, if you can factorize it from there, good. If you can use quadratic formula, that's fine. So can I simplify it initially? Let's see, and that's what I'm saying. They're giving you a choice here. You solve it by any method that's legal. So, but I notice the numbers are all divisible by 6. So that's exactly what I'm going to do here. Because I'm allowed, I've got 0 on the other side. So with x squared take away 5x plus 6, I think I can factorise that. If you want to use the quadratic formula, then do so. I've factorised it. So you get one bracket times another bracket equals 0. So take the contents, make both of them equal to 0 and solve. So here, looks like we've got two critical values. X is 2 and x is 3. Good. In the last example, we only had 1. So we're going to take these two examples and set up a nature table. It's going to be a little bit bigger here. And so can you leave space between the critical values, because we need to go and pick numbers, x numbers. So between 2 and 3, I'll probably pick 2.5. And to the left of 2, I'll probably pick 1. And to the right of 3, I'll probably pick 4. Let's see. And what we're going to do, we're just going to pop them into the derivative. So yeah, 1, 2.5 and 4. But like I said, any numbers you want. But watch between 2 and 3. Don't put 9.7, because that's not between 2 and 3. Don't pick 2.0 or 3.0, because they're exactly 2 and 3. Right, let's go and see what happens. Well, under 2 and 3, you know the derivative is actually 0. Right, we've got that. So it's the other three values we're interested in to put them into our derivative there. So we had the derivative. So in place of x, we'll get rid of it. Just put in my first number as 1. Just want an answer here. Next one, put in 2.5. We're getting a nice answer there. Might give you -3/2, that's fine. It's the signs we're interested in. There's the final one. So when x is equal to 4, we've got that there. +12. Right. So please note, it's the signs I'm interested in, the signs of these numbers. So that's kind of telling you what's happening with the curve here. So we're taking those numbers, or sorry, their signs, and we're just going to put them in there in the row that has our derivative, because that's what we just worked out. So just put those signs in there. So they're coming from the answers we had there. And then we're just going to look at the nature here. So I'm just going to go from left to right. So under where x was equal to 1, we had a positive. So a line which has a positive gradient is kind of rising up left to right. Next one, we're going to cross to that. Under 2, we've got the derivative was 0. So if that was the case, you'd be going across. The next one is negative. It would be sloping down left to right. We're hitting 0 again next. That's going to be horizontal. Right, what's happening? What is happening here? Apologies, folks. And next, positive gradient, yeah, we're going up. So what we're looking at here, underneath 2 and 3, well, it looks like under 2, if you look either side, that kind of indicates we've got a maximum here. So I'm just looking locally, and what I mean by locally, it's just I'm just looking either side, okay, where it is horizontal. So that's why I'm getting the maximum there. And next one there, it's saying we're getting a minimum here, and so because this is the region that we're actually looking at there, so locally, that's a minimum. Yeah, okay, right. I'm fine with that. So with two critical values, and at 1 underneath 2 with a maximum at 2, and underneath 3 with a minimum. Okay, right, moving swiftly on. Do you notice we started initially we started with our first function, it was x squared. The next one moved on to it was x cubed, and this one is going up to x to the 4. That's fine. So we're just going to go through it again. So go and take the function, differentiate it. Okay. Right. So here, we've got a derivative. We need the condition. Here's the condition for stationary points. The derivative is equal to 0. So go and take 4x cubed, take away 16x, and make it equal to 0. Right, we're done. Right, so we've got a cubic equation here. Cubic because it's 3. Can we solve this? Well, it looks like we can take out a common factor of x. Okay, or sorry, 4x. Take that out, yeah, because 4 goes into 16 or -16. And it looks like contents of the bracket x squared take away 4. That's a difference of 2 squares, so I can factorise that. So, or you could just solve for x, but just remember here, this is a quadratic, so we're going to have and we've got a square root, we're going to have a positive and negative answer. Positive and negative 2. So well, it looks like we get 3 solutions here, or 3, which are the critical values at -2, 0, and 2. Okay, so we're going to take these and put them into a nature table. These nature tables are going to get bigger and bigger. So we'll get 3 values here. There's your nature table. -2, 0, and 2. And look, I've left little spaces in the x row. So I'm just going to pick numbers for them. So again, you pick any numbers you want here. Pick nice numbers. And so I've set them up. So I've got 3 chosen values of x here that I need to examine. I need to pop them into the derivatives here. So, but underneath, you know right away, underneath the critical values, you know the derivative is 0. So let's go and get the derivative and put in our chosen numbers of -3, -1, 1, and 3. Okay, so just remember your derivative was 4x cubed, take away 16x. So just put them in and get our answer there. So negative 60. So the next one, put in negative 1, what's the answer? Positive 12. Next one, put in positive 1, answer, it's negative 12. Next one, put in 3, answer is positive 60. So it's the signs of the answers you're interested in. Okay, and we'll put them into the derivative row. Okay, so I'm just going to take those signs here and just pop them in. Okay, so let's look here. Yep, negative, positive, negative, positive. Okay, let's go and look at the nature of the shape. I'm going underneath x is equal to negative 3 here. We've got a negative, and again, a line with a negative gradient, be sloping that way. Next one, 0, we're going to cross. Positive, we're going up left to right. 0, we're going to cross. Next one's negative, top left to bottom right. Next one's 0, it's horizontal, and last one's positive, bottom left up to top right. So that looks, that's an imitation of the curve where the critical values are collected. So we're just going to look at these here, and looks like we've got a minimum at x equals 2, maximum at x equals 0, and a minimum at x equals positive 2. Okay, right. So that's one way where we used a nature table, but some people find that quite laborious, but it always works. It always works. Some other people, they use a thing called the second derivative test. Well, you know how to find the first derivative, and actually, you know how to find the second derivative, because you know how to differentiate. So, when you've found your second derivative, I'm using y double dash, that means my second derivative. So if the answer is greater than 0, it means it's positive. You have a minimum turning point. Okay, that's when y double dash is evaluated at the critical value of x that you've found. If, however, y double dash, the second derivative, is less than 0, which means it's negative, we say it's got a maximum turning point there. Okay, right, so if the second derivative, when it's evaluated at the critical value, is positive, we have a minimum turning point. If, however, the second derivative, when evaluated at the critical value, is negative, less than 0, we have a maximum turning point. But we haven't accounted for what happens if the second derivative, when you evaluate it at the critical value, is exactly 0. Well, you have to resort to a nature table because it doesn't tell you anything about it. Right. So that's why you'll become familiar with where you can, where you can't use the second derivative test. So I'm just going to give you a little example here. So here, x to the 4 take away 8x squared. We looked at that earlier. That's my first derivative. Okay, let's go for the second derivative. Okay, that's my second derivative. Let's use the second derivative test here. So I already had the critical values of negative 2 and 0 and positive 2. So I'm going to put in and see what answers they come up with here. So there's my first one, goes into the second derivative. It's a positive answer. Okay, this is the way we can remember here. That's a positive answer. So just think of being positive. Right, there's my wee smiley face. So positive. So that looks as if it's got a minimum turning point. So that's what I've went for there. So it's a minimum turning point. Next one, I'm putting in 0 because it's my critical value. I'm getting a negative answer. So we're going to use this the facial expression here. So if you're negative, you're no happy. So like that there. So that would kind of indicate maybe a maximum turning point there. Okay. And finally, the last value is positive 2. Put in positive 2. And we get an answer of positive 32. Well, that's positive. So let's use these little facial expressions here. So if you're positive, that's what you're looking like there. So positive, it means you've got a minimum turning point in that there. So you've seen how quick that second derivative test actually is, as opposed to the nature table. Okay. yeah, let's look at this function here. Negative 16x to the power 6. Right, I know what that looks like. I know it kind of, it looks almost parabolic. Okay, it's almost parabolic, and it's actually got um, a maximum turning point, and there's only one here. There's only one critical value, right? So I just so happens I'm familiar with the curves. Okay, right. Okay, let's. There's my first derivative. Okay, and then there's my second derivative. So the second derivative test. So I need my critical value here. So right, but so to get the critical value, we take the first derivative and make that equal to 0. Okay, so make that equal to 0 and just go and solve for x. So that'd be 0 divided by negative 96, and then we take the fifth root of 0. So we'd end up with that answer there. I'll let you go and have a wee think about how I got to x equals 0. So that's my critical value there. So I'm going to take that critical value and pop it into my second derivative test, because that's the whole point of this. So I've got my second derivative test, negative 480 times x to the power 4. Pop in x, okay, and evaluate. Oh, second derivative test throws up 0. That's no good. So there you go. It's failed. Okay, so you need to resort to a nature table. I'm going to leave that here. So when we come to the optimization, this is where we're going to use this here. Either a nature table or second derivative test. Okay, so just remember, if that was too fast, you can always rewind. Right, bye for now, folks.